A few years ago, I sort of moved to detection. So Countercept is something we set up as in part of MWR that was geared around attack detection. And it was, partly because we saw, at least in the industry, detection it was so far behind prevention. Not that prevention was necessarily working, so to speak, but at least when we were doing targeted attack simulations and so forth, we had to get around preventative controls, and we normally would, but detection, it wasn't even really anything we thought about. It wasn't even an obstacle as such. So, we thought maybe we should branch out into this area ourselves. So, even with that in mind, what I do now, something we call threat hunting. So it's very threat hunting focused. So I see machine learning as a sort of a tool in a wider tool set of things I can use within that area where it makes sense to. So in security, people often talk about something we call the cyber kill chain. So at least from the offensive standpoint, the red chain was popularized by, I think it was Lockheed Martin a few years back, but it was sort of dividing the stages of attack up into different areas and then trying to reason about what we can do to disrupt different parts of that chain. And more recently, some guys from Microsoft that have been doing some really good work in detection sort of made a blue team equivalent of this and lined them up. And then what we have here is our job in cybersecurity, at least from a detection and response perspective, is that we've got a window of opportunity there. And pretty much we need to execute our kill chain quicker than the bad guys execute theirs. And that's the sort of idea. So how does ML fit into all of this? There's a fair amount of academic literature out there around sort of intrusion detection or malware detection. I'd say that, generally speaking, a lot of this doesn't translate particularly well to real-world security. The difference between enterprise environments and the lab, so to speak, are so greatly different in security. It doesn't always translate very well. So, for example, a lot of the traditional network IDS type work that you'll see in academic literature often uses a data set from the KDD Cup back in 1999. It's an outdated data set for a start. The sort of attacks in there are attacks from 1999, and most of them don't apply now. It's also, there's a lot of synthetic data set in there, and it's labeled as well. And realistically, in an enterprise environment, that's never something we could do. We can't go and label every packet and every traffic flow as being good or bad and sort of learn on that. So it's really interesting from a perspective of benchmarking, and there's a fixed data set, and people always trying different approaches and algorithms using this, and then you can see how they perform comparatively. But it doesn't really translate to real-world security very well. And on the sort of malware detection side, people are using things in this space as well. I noticed a tweet recently where someone was commenting about this from the AV industry. Someone published a new paper on this about their detection rate with malware. There was sort of an 8% false positive rate. From an academic perspective, it's interesting, but in the real world, if you had antivirus that was actively blocking things from running and you had an 8% false positive rate, it's just completely unusable at that point. And they were comparing to what the sort of AV industry itself was doing and how their false positive rate was so tiny. So there are interesting elements to take from academia in this space. But in terms of the area I'm in, the sort of practical enterprise level security, it's more industry focused, as probably would be expected. So where's the industry focus here? Broadly speaking, I'd say at the moment most focus, if you look across different sort of product sets that are available and what people are talking about that relate to machine learning and cybersecurity, it normally divides into one of sort of two categories. So, similar to what I was just discussing before, we have what people are now terming Nextgen antivirus, which generally just means it's the same old problem. It's an antivirus technology, but they're focusing on ML as the way of implementing it rather than more traditional signature-orientated techniques or heuristic techniques. So typically speaking here, we've got something that's normally endpoint focused, sometimes mail gateway focused as well, but typically endpoint focused, obviously very malware focused rather than any other type of security data. And that's generally sort of focused on those earlier stages of the kill chain. So if you're thinking about it from a perspective of a group launching a targeted attack against a large enterprise. It's that stage of them initially making their first compromises on a network, gaining control of individual systems, and then trying to use those, that sort of foothold to then move around the network. But also, there's something that's been termed as UEBA, User and Entity Behavior Analytics. This tends to be quite network-focused, but often log-focused as well, whatever log sources you can get your hands on that might be interesting. But I mean, there are people in this space that make products that are purely based on passive network sniffing. So it maps to that traditional intrusion detection system sort of space, but tends to be ML-focused, and really that's more the later stages of the kill chain. So we're not necessarily looking for malware here. What we're looking for is what might be considered anomalous behavior that could be malicious. So, a user that suddenly goes way outside of their normal behavior pattern and starts accessing all sorts of things that they don't normally do. That's the general idea here. So that's later stages of the kill chain that tends to be focused on once someone's already on your network, and then what they do when they start moving around and abusing privileges. So what's the approach for Nextgen antivirus? I mean, the approach is very similar to traditional antivirus, just with ML as the implementation. So, it's effectively a supervised learning technique. We say, okay, there's all this malware here, and then there's all this legitimate software here, and we want to learn the difference. So, at one level, it's a very simple two-class classification problem. So, we've got different data sets for those, and there's a lot of data available too. There are some inherent problems with this, not that they can't necessarily be overcome, but for a start, you've got potentially high-dimensional data to deal with. So if you imagine if we looked specifically just at native executables, which is where a lot of antivirus technology in the past has focused, if we consider a compiled application in native code, how do you describe an executable? It's obviously a very complicated piece of data. There's a lot of assembly that's gone in, assembly language in there once it's compiled down that describes what it does. But how do you describe that in a simpler way that is still meaningful? You can't just represent it through a couple of numbers. So it's something that you need quite high-dimensional data potentially to deal with. But on the other hand, we do have millions and millions of samples of malicious software out there. So in terms of the whole curse of dimensionality and ensuring that if it's high-dimensional that we've got a good representative set, there is actually a lot of data to work with. On the sort of legitimate software side, we've actually got also a hell of a lot of data to work with. I think the problem here really is sourcing all of it. Like, obviously, it's quite simple to say, okay, well, we need the Microsoft Office suite in our set. We need all the whatever executables are installed on Windows by default, or Adobe Reader. That's going to be important, and lots more common enterprise backup software. There's loads of things we can put in there, but actually sourcing everything you're likely to encounter when you deploy technology like this to any network is unrealistic. You're always going to be encountering things that are benign, but you've never seen before and might be quite fundamentally different. So that is in itself a problem as well. So if we consider some examples here, what's this good for? What's this bad for? Let's take a very well-known malware family. I'm using Andromeda as an example of a known malware family. If we had a brand new variant come out, potentially it evades the signatures in traditional antivirus technology. Hopefully an approach like this, we might, if optimistically say that it may be that the generic traits of it under the hood that the model's picked up on have not changed significantly, and although it's new, it's still able to identify that. And we obviously had a very good representation of data in this family to work with before. So that's where we'd expect it to work well, sort of this commodity malware coming our way. But what about malicious use of legitimate software? This is where the idea of it sort of breaks down here, because there's a lot of dual-purpose tools there. Is an SSH client malicious? It's an administration tool. Your administrator is going to use it, but someone with malice in mind can use it in a bad way. And this actually is quite a common problem in the cybersecurity space, is that it's very hard to judge intent, but actually that's what we really do want to measure. It's like, is someone doing something we consider bad? But we can't necessarily directly measure that. We can sort of say, okay, well, there might be behavioral traits associated with that, but it's not, we're never 100% measuring what we really care about. but also, for example, bespoke malware used in targeted attacks. The idea here is that it might be anomalous compared to what we've seen before, but the idea is we probably have never seen anything like it before because someone has custom-made this to hit a target, and they're trying to make sure no one gets their hands on it, which is very different to your sort of common banking Trojans and Bitcoin miners or other sorts of malware that go around that are just spread widely and inherently will end up in the hands of researchers. Our model will have never seen anything like it, so it's kind of non-representative sampling here, and it's actually in the interest of someone developing this to make it look as legit as possible, make it look more close to benign software, so it's more likely to be considered okay and not be picked up by a model like this. So, in this space, actually, although we're not an antivirus company and we never really had any aspirations to do this, by a few strange sequences of events, we ended up half sort of putting one foot in that space and developed specifically a ransomware-orientated protection solution. So if you consider, if you have a general antivirus solution, actually when you start from the very question, it's not easy to answer. What is malware? It's actually not, it sounds intuitive, like, well, obviously it's something that does something bad, but it's actually not easy to give a quite concise description of it. I mean, when you consider those dual-purpose tools, it's often the intent behind it. You could say, oh, well, it allows remote access to my system, but so does TeamViewer that someone uses legitimately, for example. You can say, oh, it uploads lots of my private data to the internet, so does Dropbox. It's all the intent behind it. Ransomware was something we actually thought was a much easier to define problem, because ransomware, encrypts all your data files and then tries to get a ransom out of you. And actually the behavior associated with that, when we sort of looked across all the families out there, was relatively well defined. So, we developed a solution that monitors system behavior, and we adopted this approach of modeling benign software and known ransomware families. And then effectively we had something that was better tuned specifically for that problem. And we didn't have to worry about the wider, harder problem of general anything that's malware that's bad. So, I think we model approximately 45 features based on the behavioral traits we're measuring. So it'd be things like, oh, does it enumerate the file system? Does it write in what looks like high entropy data to disk, overwriting existing file? There's lots of different features in there. Now, if you use PCA and reduce that down to 3 dimensions, you can kind of visualize the boundaries there, and that's kind of what it looks like on screen. And I think we use a support vector machine for that. And that's actually been quite good for us. But I mean, we've had false positives with it ourselves. I mean, I think the first one in the lab was, I believe, KeyPass. I don't know if anyone uses that here, but it's a password management software. But it writes extensions with like .lock on it, like the Locky ransomware family does, and it's high entropy data, and it's overwriting existing ones. And there's lots of things about it that actually, were quite similar. But I think once we started deploying into the real world, I mean, we found some really esoteric examples. Like I think we found some soil analysis software at one company or something. I don't know what it was doing, but apparently our model thought it was ransomware. But there are people in this space focusing on the wider AV solution, where that's all they do as the company. As so for us, it was kind of a one foot in the water, but wasn't really our focus. They have problems with false positives too, and this was an interesting one a couple of months ago. Someone posted to Twitter and was like, hey, I compiled a Hello World application and I submitted it to VirusTotal, and all the ML-based solutions said it was malicious. Obviously, anyone that's written a line of code before can look at that and say, no, it's fine, it's okay. Maybe it's a bit weird that it's there, but it's not malicious. But it's like they have their own problems too, and I think in this case, some of them came back with explanations saying, oh, well, it's because actually it's shared more in common, as you'd expect, with certain malware, in that it didn't, import or export many functions, and it was very simple, and kind of, that's often one of the things that's associated with certain malware families. But whatever, I mean, the whole point there is that, it's clearly not malicious, it's saying it was, and it's one of the issues we have in this area. So, I mean, I've sort of touched on this previously, but the other problem in security is we're fundamentally dealing with an adversarial approach. We've got someone that's trying to make us fail, which isn't always the case in other applications. So I don't know if anyone's seen this research with image recognition. It's not really my area, but I thought it was really interesting. Obviously, the model in this case is looking at that image in a completely different way to obviously the human does, because we can't even tell the difference looking at those two images, but someone's been able to convince the model that that's a given by applying a noise filter. But I mean, we have the same problem in security. We've got attackers that are actively trying to bypass what we do. Now, when I was in the offensive space, I mean, any time I was doing a targeted attack, I'd make sure payloads I was using wouldn't be picked up by AV, and ideally I'd find out specifically what AV someone was using and make sure that wasn't going to be picked up. Machine learning hasn't changed that. Like, just because an ML solution's come along, I'm still going to do the same thing. And if I can make it bypass it, then I'll bypass it in the lab beforehand. And typically most of these things are, commercially available software that you can get yourself, and then you can test it in a lab before you even try and go after someone to make sure that you're, if this is a targeted attack scenario. So the sort of AV solution, it's good for that sort of commodity stuff, the stuff that's going around a lot and isn't necessarily targeted, but when you get to the more sophisticated targeted attacks, it's not necessarily that helpful. And that's the space that I operate in. So moving on, UEBA. This is arguably a much harder problem, actually. The idea here is generally people are modeling network or log data in a time series manner. And the idea is to sort of learn normal patterns and detect anomalies. So generally speaking, this is more of an unsupervised approach. We don't have labeled data. Every network's different. But what we might be able to do is, with some sort of rolling window of looking at that data, is sort of get an idea of what a baseline is with regard to whatever particular use case we want to execute, and then try and spot anomalies. So if a lot of what we do in security is look at a network this way, so we look across the network and find anomalies, as in, oh, okay, there's all these systems here that look quite common, and then there's these system administrators here, but oh, there's this one weird system here that's got some malware on it. Pretty much this space is turning that on its head and saying, okay, this behavior may not be implicitly unexpected or malicious for this network, but actually that particular system, for example, doesn't normally behave this way. Normally it's these two systems that behave this way, but today suddenly this one's doing it. And so we're not necessarily looking for malware, we're looking for really theft of credentials or unexpected behavior of systems that could be malicious, potentially. So, malicious use cases, there's lots of things you could map into this space. Generally speaking, some of the key areas are, as you see on the slides here, so when people are conducting internal network recon, port scanning, DNS enumeration, more modern techniques would be sort of mapping Active Directory through lots of LDAP queries and mining data from there. Lateral movement, which is what we mean when we've compromised one system and then we find ways of moving around on the internal network to get to other systems to achieve our objectives. And then sort of otherwise, if it's assuming it's an external orientated attack, it's then how do we get the data out of that environment and how do we control it? So we need some sort of command and control channel to control the different systems that we have access to on what's probably a firewalled network. And we also, potentially, depending on what we're after, we might want to steal data. It could be large, so we might need to transfer a significant amount of data out of the network. So, we're looking for unusually large data transfers or like very regular communications with particular systems that appear anomalous on the network, that have cropped up that not many other systems are communicating with, that kind of thing. So that's the general area that people are using this for. And there's some really significant problems here. For a start, sample size is a real issue. If you want to model an individual IP address on your network, for example, or just an individual user, you can't sort of say, okay, well, if you've got a customer, we're going to give you this. We'll just model your network for 2 years and then it'll be good. They've got to wait 2 years to get the results. Like a week, 2 weeks, even a month maybe is a bit more reasonable before it can get in place, but it needs to be something that can adapt quite quickly. And if you think just yourselves, think about what you do in your daily job. If someone was observing the network communications from your laptop, for example, do you think a week would be long enough to learn what you do? Or do you think after that, you'd be regularly doing things that you've not necessarily done before? For example, everyone may communicate with the email server that they use every day and maybe an IM service, maybe a common file share. there's all sorts of things on enterprise networks that people don't make use of very often, but are perfectly okay. That makes it difficult. DHCP makes it difficult. IP addresses change. If you can't 100% link up DHCP traffic and IP addresses, so you know exactly which system was taking that IP address at that time, then you start blurring the lines and you misidentify something because you thought this was user A before, but actually it's now user B, and as such, you'd expect its behavior to change. You've got mobile users that move around, go between offices, that connect over VPN, that then go into a different office, that then fly to another office. You've got hot desking environments where no one even uses the same computer every day, and the only way you know which one they're going to use is if you had a camera watching which desk they happen to go and sit at that day. And even just getting all the data is a problem. Like getting network data in core locations is a bit more achievable, but getting it all the way out to the edge so you've got all workstation to workstation traffic and everything is actually a real difficult challenge in a large global organization. And finally, you've even got non-learnable problems. For example, someone's stealing data. If that data is small and you're relying on saying, oh, well, I can detect anomalously large data transfers out of my network, but they're stealing something that's like a financial report that's 3 meg. You're not going to see it. So it's a very challenging area. To sort of give an idea of that, talking about, say, the IP problem, this is event activity from a machine account that was associated with an email server, if I remember rightly. Over time, the color indicates the IP address. So in this case, there's one color. You can see that it's operating from one IP, which is fine. So if in that example, hopefully you could learn that's normal. Maybe if it suddenly crops up somewhere else, it is something that would need investigation. But if we look at a user, for example, we get something that looks like this. Say it's much harder to predict. Every different color, they're constantly getting different IP addresses coming from different locations. Sometimes they're even overlapping. As a general rule of thumb, we might be able to learn that, okay, they tend to only occupy one IP address at a time, but it's a much harder problem. So one thing we can do, we can try to learn IPs, but we can also look at subnets, for example. We can say that often in an enterprise, a subnet has a defined role. It might be a server subnet that is for a particular type of server, or it might be a sort of end-user workstation subnet, and it may be that traffic patterns on a particular subnet tend to follow a different rule. And then we don't need to worry so much about IP addresses moving around, and we've actually got a lot of more data to work with then. So if there's 100 users on a particular subnet, if we're looking at a week's worth of data, we've got a much better sample size to work with. So we can take that approach. We've done it ourselves for some things. And actually there, if you look, this is given the outbound transfer volume idea. We get something that is, you can kind of intuitively see there that we've kind of got maybe one type of cluster of data, and you can clearly see the weekends where no one's in the office, or few people are in the office, where there's sort of gaps. And there's like some anomalies there, but things cluster, at least if we're looking at the data in that way. If you look at it in a histogram, you get something that looks a bit like this. Obviously, every subnet's different. It's not the nicest distribution in the world, but it's effectively a highly skewed distribution, so you need to make sure whatever approach you take is comfortable dealing with that. But even that's not that simple. Most of the time, when I've looked, I find generally for the way we slice the data for different types of use cases we want to execute, you'll find that, generally speaking, things fit into this kind of distribution. But sometimes you'll find there are independent clusters. There are two different things going on. Or maybe you've, because you don't have perfect subnet data, you've effectively maybe treated two subnets as one because you don't know 100% where the boundaries are. So, in the early days, I was trying to find a one-size-fits-all solution, and this is only single-dimensional data, but I've just got it plotted two-dimensional to make it a bit easier to see. But in this case, we had two backup systems on the right and the left that were transferring far larger data quantities out of that subnet than everything else. And I thought, well, at least if you could learn multiple clusters, then you could at least have a better idea there. And that was me using a one-class support vector machine to do that. But this thing is, with things like clustering algorithms, normally there's certain assumptions you have to make. Oh, you need to know roughly how many clusters there are, or they have to be, roughly the same size. I mean, different algorithms have different types of applications for this. When you basically don't know any of these things at all, it gets pretty difficult. So I don't know if there's going to be clusters or how many, and there's too much data for us to be sort of working this out manually all the time to tune things. It has to be something that's automated. So actually dealing with this problem is actually very challenging. But sometimes it does work. So for example, I've just filtered out from some of our data sets one particular example from our network. But here we've identified a particular IP address that, sorry, I've blanked out some of the details. But we've identified an anomalously large data transfer out of a particular subnet. It was nearly a gig. We've got effectively a sort of anomaly measure here. So we know for that subnet roughly how anomalous it was. We've also got basic enrichment then built into that, which is what makes it much easier then for humans to consume. So although possible sources is unknown, which means it wasn't able to correlate that IP against any other event data to give more context on who the user might be, for example. But at least on the IPs, it was able to correlate against DNS traffic and see that that was TeamViewer. So then I've immediately got something better to work with at that point. On the user side, it's slightly different, because here we're not really dealing with continuous data, so to speak. If we want to just, it's more categorical at this point. If we were saying, what systems does a user normally operate from that we could call a source? Like, I log into my laptop, that's a source for me. And then maybe I access a file server, an email server, an internal wiki, for example, and that services I access. You can kind of, if you were to simplify it down to that level, you could do it in a very simple two-dimensional sort of model. There are lots of different types of logins that actually can happen on a network, and you can be more specific than this. So you could separate based on whether it's a service account logon versus an interactive logon. There's lots more you can do here, but a lot of them broadly fall into that sort of category. So if we were to just sort of say, okay, over 30 days, what are the ones they accessed, and then if they access something they didn't normally do, then tell me about it. That's quite easy, and well, you don't need machine learning for that either. But where you can try and make it slightly more interesting is by saying, well, some users may be much more predictable than others. So maybe we can sort of split our data sets into something that we use as like a baseline, and then part of it that we actually use to sort of model how common it is to deviate from that baseline. So for example, here, if we've got part of our data, we've formed a baseline set, and then, for other days from that training set, we've kind of sort of said, well, how many things did they access that isn't on our baseline for them? Monday, Tuesday, nothing. They were well within normal. Then Wednesday, they accessed Exchange webmail, and they don't normally do that. It just happened to be they say accessed it in the evening at home. So that wasn't, it doesn't happen as often. So we can say, okay, maybe it's normal for them to access one or two things outside of a baseline, maybe learn on that boundary. And so at that point, you can even try and validate that, use validation sets, and say, over time, like if we're doing this model, can we reliably predict how much a user deviates from their baseline? And so, for example, some users may be really predictable. It may be that their job is quite specific, and they just do the same thing every day. Administrators, on the other hand, they're a nightmare because they access systems based on what breaks or what needs building, or which user emails them complaining about a problem, and without some clever way of having a data set to correlate that with, like support tickets, for example, it seems pretty unpredictable. So you might be able to either make much sort of allow more room for them to behave or misbehave, so to speak, before you get to a threshold where you say, okay, actually, we still need to look into this now. This is way beyond normal. Or you can sort of filter them out of the data set by deciding that they actually aren't predictable and as such maybe aren't good for the model. So I mean, that are sort of, broadly speaking, the main areas this tends to get used. I'm going to use one completely different example now, but just as a way of showing sometimes ML can be plugged in to solve existing other little problems in security. So right here, this is like one type of approach we use that isn't ML based, but when we're threat hunting, remember that cyber kill chain. One of those things is persistence. So generally speaking, if I compromise a laptop, if I'm on a targeted attack engagement, I don't want to lose access when they log out or they reboot their system. I want to maintain access. And there are lots of ways of achieving this. So from a threat hunter perspective, there's lots of places we like to try to look to see for evidence of people doing this. So this is a really basic example. Auto runs, there's lots of different locations in the registry. There's services, scheduled tasks. There's many ways you can do this. We gather that data from our endpoints, and then we sort of aggregate it up. And we look for anomalies, and then we also enrich that data with other sets to make it much easier to analyze. Now, effectively, this is both clustering and anomaly detection. Yeah, we are grouping things that are similar up. So we're saying, okay, this path here combined with this executable hash, group that. So that's like a cluster. How many machines was it present on? So here, maybe we've got a VPN client that everyone uses, and then I can see quite quickly, this particular path was present, but it's on 10,000 machines, and then that hash was known on VirusTotal. It's signed legitimately. I know it's the VPN client we use in my business, for example. Okay, that's fine. And on the other side, we may have anomalies where we say, okay, well, there's this one thing here. It's only on one machine. It's not cryptographically signed. In some cases, it's never been seen on VirusTotal. That doesn't mean it's bad. It just means that it's weird and no one's really seen it before. And maybe it's an anomaly I want to investigate. But we don't need machine learning because most of these things, these are well-defined boundaries. Machine learning is good for when you've got fuzzy boundaries, or you don't know where to set the threshold or what the bucket is. But this is an example of using it if you place, if your malicious scenarios, you're putting like a binary on disk, for example. There's another thing in security that people often do called living off the land, which is where we make malicious use of existing tools we expect to be there that are perfectly normal. One of the ways we look for that is a similar idea, but looking at a bunch of legitimate tools we know can be used for quite malicious purposes, and then often look in the context in which they execute, so which parent process launched them and what their command line arguments for, which may detect their behavior, and taking a similar approach. But we had a problem with this in that, I'm going to use Powershells as an example. That's really commonly used maliciously, but also used by administrators. If we had one PowerShell encoded command that was some malicious thing on one system, fine, that's an anomaly for us, and we'd look at that and say, okay, I want to investigate that. But we saw things on real networks like the bottom thing, where we had like 100,000 examples of something that was running a PowerShell script from a certain directory, but the file itself was a random GUID, and it was different every time. And in actual fact, it was being launched by Windows SCCM, which is a system deployment tool. The problem is there's this one little bit that's changing every time, so you end up, it looks like an anomaly on every system on your network rather than being able to do this bucketing strategy. So sometimes it's just, there's something that's annoying that actually that little bit we can solve with maybe some ML. So what we did with things like this was take a sort of Bagofwords approach and break up the arguments how we'd like to. So we break them up by spaces, we accommodate for double quotes, enclosing them, then we say, oh, okay, now once we've broken it up, we do a second level, because we've got paths, we might want to break those up on backslashes, we might have PowerShell codes, we want to break that up on semicolons, and then we've got a whole bunch of tokens, and we can represent these args as a vector. And the idea then is that something like these examples, you'll have this random GUID one where only one dimension differs every time between all the examples. And this does result in high-dimensional data, but it's difficult to build like a sort of word-to-vec thing if you don't have a pre-existing dictionary to go by, and like a lot of this stuff is just constant new things you've never seen before. So for example, we use like dbScan worked quite well for this, because things like k-means do not work well for this, because I have no idea how many clusters there are, I have no idea whether they're similar sizes or not, so k-means is kind of straight out. dbScan works quite well though, because I can say, well yeah, actually I can give you a minimum cluster size, that's something I think I can put a number on. And actually I can give you a minimum density, because I can control the density based on how complicated or what the number of arguments are. So if we represent things where we scale the dimensions according to how many arguments there were, and then we sort of say, I want a threshold of how similar something has to be, and then we use something like Manhattan distance, because I don't care about there's no such thing as half an argument, right? The argument's either there or it's not. It's a token that's present or it's not. So we use Manhattan distance. So we're basically just measuring how many sort of dimensional changes do you have to go through till you get to the one that's similar. And then actually we have a way of clustering these things up. And it's pretty interesting because then like that actually works quite well in a lot of cases. So, you know, the SEC example, for example, actually it was something we discovered very quickly. We could put an exception case in that. But the problem is then you get much more frequent, smaller examples of this occurring, and if you don't want to be writing exceptions in your code all the time, then you do something like this and let it handle it for you. So then we can actually put those things together and say, no, this kind of thing happened on 100,000 systems, and you've got that as one thing to review, not it was 100,000 anomalies that you've got to look through. So, probably one final point before concluding. I've probably painted the picture that machine learning isn't a like magic solution for the whole of the cybersecurity problem. It's more of an enhancement thing. But I think actually when really unexpected things happen, it's a good way of actually looking back and reviewing these types of things. So back in Easter, I don't know if any of you saw this, some of this actually made the mainstream media outside of security, but there was a whole bunch of what was portrayed to be NSA tools leaked on the internet. I spent a lot of Easter looking into that, did a lot of analysis, and wrote some scripts for detecting it. This was like an unprecedented release of really advanced stuff that was very, very cool. Now, we went through all of our detection mechanisms and like, well, you know, this is like top echelon. Would we have picked this up? And we did find a couple of techniques we had that we could use to detect it already without developing something new, but they weren't ML techniques. They were just, you know, it was domain expertise, purely. It was based on certain memory analysis techniques. And there was I didn't see anything come out of any of the ML vendors talking about how they'd already detected it. And I think sometimes unprecedented examples like this are a good way of sort of taking a check. And if you're developing solutions in the future of saying, you know, if we'd never known about this, like would our model potentially have been able to deal with something this out there? Or is it something that we're only really expecting to solve the more commodity problem here? Is it just a more efficient way of us dealing with the standard antivirus problem, for example? So, in conclusion, I'd say like ML can be useful in security. I see it getting involved a bit more, but I very much see it as an enhancement technology, not a replacement technology. So I think it's something that should be used to enhance the capabilities of a very skilled team. I don't see it just making your requirement for having a skilled cybersecurity team go away. So I just don't think it's that simple, and it's only one aspect of attack detection. There are elements where it fits in really well, and there are elements where it doesn't. But I am kind of excited to see what other things people come up with in future. But I don't see a sort of Skynet situation of one big AI controlling cybersecurity in an environment anytime soon. The other point, like probably everyone would say doing ML, is that the data is more critical. We put a lot of focus in the early days on what we do on getting the right type of data that could enable us to uncover the malicious techniques we wanted to. Whereas a lot of people often take what's effectively bad data and then chuck advanced analysis at it, hoping to get a good result in this space. And obviously, there's only so far you can take that. Like having good data with good domain expertise and simple analysis is always better than bad data and advanced analysis. Because in some cases, we can't learn from data that's not present, for example. So, there's many cases where actually just inherently the types of data people are looking at, you will not be able to spot certain types of malicious activity. And network data in particular is a bad candidate here because universal encryption has become more and more norm over time. So actually the data available to us in network traffic is going down over time. And deperimeterization means people are not all on the same network at the same time. They're kind of working at home. And so we're gradually losing data there too. So we need lots of other data sources to factor into this. But that pretty much concludes the presentation for me. Are there any